So thank you for the introduction and thanks a lot for the invitation. It's, well, for me, because it's first time I'm here, it's really a nice surprise. I expected something much smaller and well, this is really great. Okay, so today I'm going to talk about structural alphabets for conformation analysis of nucleic acids, which we use for annotation validation, modeling, and possibly refinement of nucleic acids, structures, or models. First of all, we are not going to compete with people designing bond and angles restraints. We are concentrating, looking at the structures only from the torsion point of view, which is missing, so it's actually a good niche for us. So, conformations of biomolecules. For proteins, it's kind of intuitive. Every program can show you the helices and sheets and so on. For nucleic acids, it's a bit more complicated. Here in camera figure, you can see color-coded sequence, if you remember that green is something, but that's it. You have to look at it and kind of decrypt it, that it's double helical something, DNA or RNA maybe, and it's banned. But that's basically the information about conformation we have is 0. There were or are some attempts to describe conformations based on these so-called base parameters, but I'm sorry, it's fundamentally wrong. You cannot really distinguish it based on these parameters. So, a little piece of history. Everybody who ever seen some nucleic acid knows that there are obviously A, B, and Z forms, which are occurring in double helical forms, but well, it is not exactly sufficient to describe the whole complexity of nucleic acid structures. There are quadruplexes, holiday junctions, intercalated regions, I motifs, tetraloops, and other really interesting motifs from RNA. So how do we deal with that? How do we look for conformers in the nucleic acid structures? Many people tried and failed to find it based on Cartesian coordinates because it's too noisy and you cannot efficiently cluster the data at this level. Also, there is no simple Ramachandran-like plot in 2 dimensions only. There is some attempt using these so-called eta-theta pseudo-torsions, but again, you cannot really distinguish the real conformations. So we have to kind of live with the fact that nucleic acids have many degrees of freedom, and the way how we did it, how Bohdan and Helen and some like Richardson started to look at it, is working with the sugar-phosphate backbone and its torsion angles. Because of the insufficient number of structures, we have to work with something we call STEP, which is nearly dinucleotide. It's actually missing the first phosphate. These, about 2008, the world was still kind of divided to RNA world and DNA world. RNA people designed these suites, which were described only by 7 torsions. They ignored the, or not ignored, but they didn't include the rotation of the base. So it was really looking only at the backbone. The STEP is actually including the chi-torsions. And at that time, there were 46 suites and 18 for RNA and 18 dinucleotide step conformers for DNA. So then we used basically the same technology or the level of description and designed our extended set of DNA conformations, which in the end we had 44, and it was after a long time published, unfortunately relatively recently. The whole idea is based on, we basically extract as good crystal structures from PDB, remove the sequentially redundant structures, and extract the dinucleotides, measure the torsions, and cluster them. Based on that, we designed these 44 classes and introduced two validation and annotation parameters. One we call conf, which is now a value between 0 to 100. 100 means perfect fit, 0 means outlier. And it's actually designed as a value of Gaussian function, which would kind of cover the boundaries on each torsion. The scale from 0 to 100 is just because it's then easily, you can easily visualize it in bimol or whatever. The other things are these pyramids. Their color and size can serve as simple annotation for the structure. Maybe not for you, but for me, this is obvious that it's mostly B form, but there are some pink A forms, which is actually quite surprising because this is the one BNA, this prototypical B form, right? It's not that B as many people think. 44 was at the time a bit too many, so we also designed something we call CANA, like the conformational alphabet, which grouped similar groups of conformations together. We used it, I would say, successfully to describe the behavior. For example, this bending in transcription factor complexes is actually only A forms are responsible for the bending, contrary to the DNA wrapped around the histone particle, where it's actually periodically placed special B conformation called B2. Well, nobody is impressed and nobody cites it, but I think it solved some issue which goes on for many years. So later on, actually, we are thinking, why is there really DNA and RNA different at the torsional level? And well, the answer is it's not. We can use the same technology to describe both DNA and RNA at the same time. The only thing we had to include was like 3 more parameters because the RNA structures are more complicated. So we had to include something which controls the distance and relative orientation of the bases. So now we are doing everything in 12-dimensional space. Again, we extracted relatively high resolution data and ended up with 96 classes which can describe any nucleic acid. Because there are some open, and open means that they are kind of pointing, the bases are pointing in different directions or intercalated. We also increased the number of alphabet letters. Then, when we had this technology, we looked at all the structures containing nucleic acids in the PDB, which is now over 11,000 structures containing around 6 million steps. And if you assign it, you will see that 30% of this data is unassigned. There are outliers according to our classification. People don't like this number, as expected. So does it mean that most of these 30% unassigned steps are errors? I'll try to, well, the answer is mostly yes, but I'll try to explain why. we'll have to start with the assigned conformation. So these are data. This is correlation for Euclidean distance with the Rispes correlation coefficient for the canonical A conformation for data worse than 2.5 angstrom resolution. So in this lower right corner, you can see that most of the data is supported by the data, and the distance from the reference is relatively small. This is the measure we are using for the assignment. So as some kind of internal proof or validation of it, we are also plotting the same for RMSD with respect to the best representative of the class. Again, the RMSDs are relatively small. Here, this kind of tail, it shows that the conformations are correct there. It is really nicely looking A geometry, but it's not really supported by data. In this low resolution, it's around 20%. If you look at the same thing, only better than 1.5 angstrom resolution, so really high resolution data, situation improves, and most of this noise actually disappeared, and really over 90% of the data is in like close to what it should be and supported by the experimental density. So then, similar plot, but for the unassigned, for the outliers. So in the torsional space or in the Cartesian space, you can see that majority of the data is here, but it's a bit farther, so more than 0.5 angstrom. The left part, at high resolution, we can again ignore, it's relatively small. This is a result of one of the atoms of the 18 atoms we are using of the backbone is basically not in the density, and when you average it, it goes there. Interesting thing is here, this 1/3 or 20%, depending at which level you look at it. It contains something which is supported by the data, but far from our known clusters. It most probably contains real conformations which have some function, and they are unique. But if you look at the count, this is only 300, 200 high resolution representatives. And so far, it's not enough to extend our 96 classes and define new ones, which can serve as a seed for new conformational classes. Then this 70 or 50% of the data is actually suspiciously close to what we know. And we didn't do it for all structures, but for some we did try to help it reach the most similar conformation, and it actually goes there. So many of them can be saved and corrected. So it's a bit more wider for this high resolution, but again, in the left part, it's basically the resolution effect. This, the ratio here is basically similar, I would say, more or less. So yes, the answer is there are mostly errors, but can be corrected. So I would say that's good news. So what are we using NTCs for? As I said, for the annotation and validation, we designed this graphical representation and the confold score, which shows you the quality of the data. And now we are working on designing restraints for refinement with collaboration with Phoenix and FMAC people. It kind of works already, but it still has to be polished for general public, I would say. Then we also use our conformation classes in MMB, de novo modeling and fitting to density, and in the enhanced sampling. which is kind of overlooked. You can get much easier publication when you say, okay, so I simulated few microseconds using classical MD. Nobody cares that the ensemble of the structures is wrong. We can simulate only a few tenths of nanoseconds, and the partitioning of the conformations is correct, but yeah, we ended up in this not so great journal. So we developed or are developing a web service for the users to give them the opportunity to look at their own structures or analyze structures from the WPDB or PDB redo. And it's available at denatco.org. And I wanted to show you some demo, but I didn't make it in time. So sorry. So if you want to see it in action, let me know, or just open this web page. The thing is that I wanted to show you the devel version, which includes some new development. We added support for density maps. We introduced something we call connectivity. So how well the overlapping dinucleotides actually combine to form the whole structure. So we are trying to go back to the tetranucleotide description, which will be better. And it also provides these user adjustable restraints parameters. And everything is working safe, and we are actually using the, no, I forgot the name. Oh, yeah, really, I forgot it. Well, I wanted to answer the question, what are the tools to convert PDB to safe? We are using it on the web, Maxit, developed at the Rutgers University. And yeah, and we are planning to move from JMOL to MolStar because it will be much faster. Okay, thanks.
Thank you, Jurka. We have time for questions. Are there any? Can I see something down? Okay, I'll do this one down here.
Are there?
Could you say anything about if you've got a DNA intercalating drug, do you get a standard step, or is there a lot of variation in that?
Sorry?
If you have a DNA intercalating drug, a compound between two bases, does that give you a standard geometry, or is there variation in that?
Yeah, this is one of the representative of the intercalated conformation, and they are surprisingly the same. It doesn't really matter if you have an RNA base from the other strand or a drug or something.
Hi, so you said that your simulated DNA ensembles were not right. Can you say something else about that? What force fields were we using? How were you doing the sampling? Yeah,
our ensemble was better than how other people do it, because we actually used potential of mean force derived from the assigned conformation. So we basically threw away this 30% of noise and derived the edit potential only on the clean data. And then it works much better.
Okay.
And it's actually quite cheap.
Okay, okay, thank you.
We are working on something similar for proteins, but it's not ready yet.
Okay, thank you.